this video is going to be a pretty comprehensive guide on the technique of partial fractions in the context of integration. Because it's going to be a pretty long video, I'm going to start off with an outline of what I'll cover, and I'll hyperlink each of these things in the description in case you want to skip to a particular kind of example. Anyway, here's the game plan. I'm going to start off by just generally talking about the point of partial fractions, or what it is, or where it fits in the context of integration. And then I have 5 different examples planned to cover pretty much any kind of complication that can arise when you're doing partial fractions problems. So, what is partial fractions? Here's chalk. The reason why I want to talk about this is because a lot of times when you learn about partial fractions for the first time, it's in an integration class or it's in a Calc 2 class and you're learning it in the context of integration. It's presented as a technique of integration. It's not. Partial fractions is just algebra. That's really important to keep in mind just so that you don't get confused and intimidated, by the problems. So write that down. Partial fractions is just algebra. It's simply an algebraic process of taking a complicated looking fraction of polynomials and breaking them up into simpler, easier fractions to work with. So I'm going to give you a silly metaphor, which might seem a little ridiculous, but it captures the spirit of what we're doing. Suppose I walked up to you and I gave you the expression 1/2 minus 1/3, and I said simplify it as much as you can. No problem. We know how to add fractions together. If I wanted to add these two fractions, what would I do? I would find a common denominator. That common denominator is 2 times 3. Then in the numerator, I'll have to multiply here by 3, multiply here by 2. We'll get 3 minus 2. And so it looks like this is 1/6. Okay. Pretty deep fact. Exciting stuff we're doing here. Why am I talking about this? Here's what partial fractions is. Partial fractions is going in the reverse direction. That's it. In particular, what if instead someone walked up to you on the street and gave you the fraction 1/6, and you looked at it and you thought, oh my God, 6 is such a big number. This is really scary to me. I don't know what's going on. If only I could take this really scary looking fraction and break it up into simpler fractions. What would you do? Well, you'd probably say, I have my scary looking fraction. I know I can factor the bottom, like 2 times 3. And motivated by what we did here, if this was going to be broken up into simpler fractions, it would probably look like something over 2 and something over 3. The problem with going this direction as opposed to the direction that we did up here is when you go this way, it's hard to eyeball what these two things are. And in general, you want a decomposition like this, but you don't quite know like what numbers you put here and here. So these are unknowns. The process of partial fractions is just determining what these unknown numbers are. But then once you do that, you'll have your scary looking fraction decomposed into simpler pieces. So it's a little silly to do this with just numerical fractions, but like I said, it captures the spirit of partial fractions. So let me write that down. So this process here is exactly what partial fractions is. The only difference is that we're going to be doing this with fractions of polynomials. So for us, partial fractions is the process of and again, it's just algebra, no calculus involved at all, is the algebraic process of decomposing rational functions. What was a rational function? To recall, that just means it's a fraction of polynomials. So I don't know, x plus 3 over x squared plus 2x plus 1, something like that. We get a scary looking rational expression, and we just want to decompose it into simpler pieces. The process of decomposing rational functions into simpler pieces. I may have spelled this right, maybe not. Simpler fractions, let's go with that. A word I definitely know how to spell. And again, the idea is if I had to integrate this, maybe I don't know what to do. Maybe, maybe not. It might be easier if we split it up into simple fractions. Okay. That's the goal of this video. The details of all of this are going to be in these examples. Okay, so to begin studying the technique of partial fractions, we'll start with an example. Like I mentioned, partial fractions itself doesn't have anything to do with integration, but the main reason we learn it is to deal with integrals like this. So we'll start working through this example and we'll see some of the ideas and the techniques in the process of doing so. Now, given an integral, in our case, 3x plus 3 over x squared plus x minus 2. Before I start thinking about any other kind of technique like partial fractions or integration by parts or anything fancy like that, the first question I'm asking myself is maybe we don't need to do that. And I wouldn't have written this example if we could, but just for fun, let's think, could we do a simple substitution? Well, if there was a simple substitution we could do, it would probably be to call the denominator u. If anything would work, that's the kind of thing we want to do. And you could try, but the du in that case would be 2x plus 1, and that doesn't match up so well with the numerator, so it probably won't work very well. Okay, so then we're screwed. So what do we do? This is where partial fractions comes in. I look at this, and I think, this is a really complicated, maybe, rational expression. Maybe I can decompose it into simpler pieces, just like we did with 1/6 earlier. Okay. Now, how does this work? Motivated by the kind of common denominator stuff I talked about a minute ago, I'll begin with the rational expression, and then I think if I have any hope of splitting this up into simpler pieces, I need to factor the denominator. That's going to determine how these things are split up. So every time you do a partial fractions decomposition, your first step is to factor the denominator as much as possible. In this case, it looks like, let's see, 2 times -1 is -2, and 2 plus -1 is 1. So this should factor as x minus 1 and x plus 2, I think. And then I'll leave the top alone. Okay? Then again, motivated by what I talked about earlier, probably we want to decompose this according to these factors in the denominator. But what goes on top, we don't know. That's what we'll have to figure out. Now, one important principle to keep in mind when you do partial fractions is that the unknown expressions on top need to be So let me write this down. Unknown expressions on top should be 1 degree smaller than the degree of the factor in the denominator. That was a lot of words, and I'll write it, and it probably won't make sense, but then I'll explain what I mean. So unknown expressions on top should be 1 degree smaller than, I didn't give myself enough room, than the factor. What in the world do I mean by that? If I look at x plus 1, what is the degree of this expression? It's a 1 degree polynomial, degree 1 polynomial. That tells me that the expression on top needs to be a degree 0 polynomial. What is a degree 0 polynomial? It's just a constant. So the unknown thing that I'm going to put here in this case is just some unknown constant, which I can call A. Now, when we talk about quadratic factors in a little bit, this will look a little different, but sit tight. In this case, where you only have linear factors are degree 1, so you just need to put an unknown constant, a degree 0 thing, on top. Likewise, x plus 2 is another linear factor, degree 1, so the thing on top should be degree 0, which is another constant. Okay. This is the kind of decomposition we want, and again, the point is we don't know yet what A and B are, and all we have to do is just figure out what A and B are. That's the goal. How are we supposed to do that? We have an equation here, so let me write this down. I'll skip this step again. What we seek is this should be equal to this. Actually, let me just use this term. This is an equality of functions, and we can use that to our advantage to determine A and B. Usually your first step here is going to be to say, fractions are kind of annoying, I don't want to deal with fractions. But if I multiply both sides by the denominator here, I can clear all the denominators, and then I'll just have an expression involving polynomials. And that's usually easier to work with. So first step here is to always clear denominators. Which by that I mean multiply both sides by this quantity. On the left, if I do that, when I multiply by the denominator, it cancels out the denominator, so the only thing I'm left with is the 3x plus 3 on top. Now, multiply both sides by this denominator. When we do that to this term, this times this, the x minus 1's cancel out, and you'll just be left with an x plus 2 on top. So after multiplying through by the denominator, this term is going to become a times quantity x plus 2. Likewise with the last term, in this case the x plus 2's cancel out, so you'll be left with a b times x minus 1. Okay. This looks a lot better because now we have an equality of polynomials. Polynomials are easy to understand. Now, this can be confusing the first time you see it, but this equality, we want this to hold for all x. That's the key with these partial fractions problems. What that means is that we're allowed to plug in any x value we want here, and we should get a true equation. Typically, when you have linear factors, the best plan of attack to determine these unknown coefficients a and b is to plug in the root of one of the linear factors. So let me write that down. So a lot of thinking in this one. Another principle that I just said is that if you see linear factors, what you should do is you should plug in their roots. What do I mean by that? One of our linear factors here is, for example, x plus 2. The root of this factor is the number which makes it 0, which is negative 2. So in other words, the first thing I'm going to do is I'm going to plug in x equals negative 2 into this equation, which I'm allowed to do because this holds for all x. If I set x to be negative 2, I'll get the equation 3 times negative 2 plus 3 equals, by construction, this is 0. Negative 2 plus 2 is 0. That whole term goes away, which leaves us with b times negative 2 minus 1. And after some simplification, this will give us b. Let's see, negative 6 plus 3 is negative 3 equals b times negative 3. Solve for b, looks like b has to be 1. Nice. All right, one down, one more to go. We'll plug in the other linear factor, and a is going to pop out immediately. So this case, when you only have linear factors, is the most ideal case. It's probably the easiest one to deal with because for all of these, you can just plug in the respective roots, and it'll immediately spit out one of the coefficients. So let's do the other one. And I conveniently just erased the equation that we need to reference. So let me remind you what it is over here. It was 3x plus 3 equals a times x plus 2 plus b times x minus 1. Okay, so we plugged in negative 2. Now we need to plug in 1. If we do that, if x is 1, I'll get the equation 3 times 1 plus 3 equals a times 1 plus 3, 1 plus 2, sorry. And then again, by construction, plugging in 1 makes this entire term 0. So this is the equation we're left with. 3 plus 3 is 6. And then 1 plus 2 is 3. Solve for a. Looks like a is 2. Okay. And there we go. We've figured out both coefficients, which means we have our partial fractions decomposition. The integrand that we started with, 3x plus 3 over x squared plus x minus 2, we decomposed this into a over x minus 1. A we just figured out is 2. Plus b was 1 over x minus 2. And the point is that to integrate this, we just have to integrate this and this. And these are both very easy to do. So we can finish it off. So the integral that we care about by this decomposition is just the sum of these two integrals. Both of these are just log of absolute blah, blah, blah type things. And then we're done. So continuing from over there. Antiderivative of 2 over x minus 1 is 2 log of absolute x minus 1 plus, likewise, the antiderivative of the second one is going to be log absolute x minus 2. Add a constant. That'll do it. So, first baby example of a partial fractions decomposition. As far as partial fractions goes, this is about as straightforward as it gets. Linear factors, easy to solve, easy to decompose, easy to integrate as well. In general, things get more complicated. All right, next up is an example where we don't only have linear factors. So the first kind of complication that can arise in partial fractions is you could get factors that are quadratic that you can't factor anymore, which is indeed the case with this one. We're given an integral, x squared plus x over, and then I've factored it already for us, which is a little nice, but x minus 1 times x squared plus 1. Okay. In the previous example, I talked about how, you should think about always factoring the denominator as much as possible. The denominator is factored a little bit here. And the first thing to think about is, can we factor x squared plus 1 more? The answer is no over the real numbers, because it doesn't have any roots. It doesn't have any real roots. Sketch a graph of x squared plus 1. X squared is a happy parabola. It's shifted up by 1, so it roughly looks like this. Never crosses the x-axis, so this thing can't be factored more. In other words, this is an irreducible quadratic factor. So we're just going to have to live with it and move on to our decomposition. Okay? Well, let's proceed just like we did in the previous example. We start out by wanting to decompose this into simpler fractions. This time we have two factors again, so I want to split this up into two fractions. One of them will have a denominator of x minus 1. The other one is the irreducible quadratic factor, is x squared plus 1. Okay. This is where one of the things I talked about in the first example comes into play, which is, what do we put up here? Well, we don't know, right? That's the point. That's what we ultimately want to figure out. But what form do these unknown expressions take? I'll rewrite the key idea from last time, which is that the degree, and I'll be a little bit more brief, the degree of the top expression should be the degree of the bottom expression. And actually, ignore what I just said. I'm going to say that a little more precisely. The degree of the top expression should be 1 smaller than the degree of the bottom factor. Now, don't worry about that for now. We'll talk about this when we get to repeated factors. But the degree of the top should be 1 smaller than the degree of the bottom. Here, like in the previous example, the degree is 1. So the unknown expression that goes up top here should be 0. A degree 0 thing is just a constant. So just like before, I put an unknown constant there. Here's where things are a little different. The degree of this factor is 2. Because the degree of the factor is 2, the expression that I put in the numerator here has to be of degree 1. What does the most general possible degree 1 expression look like? It'll look like bx plus c. Bx plus c is the most general possible degree 1 expression. And we have to account for any possibility on top. Anyway, so the summary is if you have one of these irreducible quadratic factors, the thingy that you put on top should look like bx plus c. That's the takeaway. This is really the main difference from the previous example, and from here on out, it's going to be roughly the same in that all we need to do is just enough algebra to determine the now 3 unknown coefficients that we have. The first step is the same as it was in the previous example, which is I don't like fractions, so I want to multiply through by this denominator to clear all the fractions away. If I do that, again, the denominator is cleared completely on the left. On the right, multiplying by the denominator will cancel this term and then leave an x squared plus 1 next to a. And then over here, the x squared plus 1s will go away, and that'll leave me with a bx plus c quantity times x minus 1. Okay. Same situation as before. Same principle holds also in that if you have any linear factors, the first thing you should do is plug those in. We have one linear factor, x minus 1 again, so the first thing I'll do is plug in x equals 1. When x is 1, by construction, this is 0, so this whole term goes away. And we're left with 1 squared plus 1 equals a times 1 squared plus 1. Simplifying a little bit gives 2 on the left equals 2a. So therefore, it looks like a has to be 1. All right. One coefficient down. Unfortunately, now we've got 2 more to find. The other unfortunate thing about this scenario when you have irreducible quadratic factors is that we're out of linear factors to plug roots into. In the previous problem, the next thing that we did is we had this other linear factor. I plugged in the root and we were done. But I can't do that here. There's nothing I can plug in to make this 0. So we have to do something else. There's a couple things you can do. One thing you can keep in mind is that, we plugged in x equals 1 here because it seems like a smart choice. But like I talked about in the prior example, this equality holds for all x. You can plug in anything you want. Like you could plug in x equals 0. You could plug in x equals 1 billion. Probably wouldn't be very helpful to do that, but you could. So you can really do anything you want. Usually in this scenario, when I have irreducible quadratic expressions, I like to compare coefficients. Of the left and right side. The idea is that this equality that we're working with right now, this is an equality of polynomials. And if 2 polynomials are equal, their coefficients are equal. In other words, I can be pretty explicit about this by asking, what if I compare the coefficient of x squared on both sides of the equation. On the left-hand side, the coefficient in front of x squared is just 1. On the right-hand side, we have to think a little bit harder. What's the coefficient of x squared? Well, here we can get an ax squared. The only other way on the right-hand side here to get an x squared term is from the product of bx and x. So I won't do this explicitly, but if you were to multiply everything out on the right by hand, and then collect all the like terms, and then collect in particular the x squared terms, you'd have an ax squared plus bx squared which, factor out the x squared, tells you that the coefficient in front of x squared on the right is a plus b. And again, because this is an equality of polynomials, the point is that those two coefficients have to be the same. So I generate this equation, 1 equals a plus b. Now, this doesn't tell us yet what either a, oh, never mind. We already know that a is 1. Okay, so this is pretty good. I was getting ahead of myself. We know that a is 1, so therefore, it looks like b is 0. Cool. Okay, another one down. I'll do the same process to determine c. Which coefficient could I compare? You know, again, you could do whatever you want, but I can see looking at this latter product that I'll get a c times minus 1. That's a constant term. So if it were me, the next thing I would probably try to determine c, which is our remaining unknown, is I would compare the constant term of both sides. Again, on the left, this is easy. The constant term is 0 because there is no constant. This is like x squared plus x plus 0. And then on the right, I'll do the same thing that I did over here. I'll just collect all possible constants. One of them is from this term, a times 1. So that term would generate an a plus, from this term, the only way we could get a constant is exactly from that product that I observed earlier, c times negative 1. There we go, 0 equals a minus c. Again, we already know a. A was 1. So it looks like c has to be 1 as well. Okay, so we've figured out a, b, and c. Again, the general setup is the same in this scenario when we have quadratic factors. The thing that changes is, 1, the expression that goes on top of the quadratic factor. The other thing that can change is your process by actually determining the coefficients. Again, you can do whatever you want. That's the good thing about math. My preferred method of attack is to, again, plug in linear factor roots first. And then when we have the quadratic stuff, move on and compare coefficients. All right, so we know a, b, and c. So what we've found, continuing here, so a, I think I erased down here, but a was 1. B was 0, so there actually was no x term here. But there could be, so you do have to check. And then C was 1. Cool. We've decomposed it. We've done the partial fractions. Now, evaluating this integral is just a matter of evaluating these two integrals. Now, like last time, one of these is going to be a log-looking thing. In the quadratic case, you'll typically get something that looks like this. A lot of times it's going to be an arctangent type integral, which is exactly the case here. Okay, so again, like last time, the antiderivative here is log of absolute x minus 1. Plus, here, you could either do a trig substitution here, or you could just remember that the derivative of arctangent is exactly 1 over x squared plus 1. So therefore, the antiderivative of 1 over x squared plus 1 is arctangent. Throw in a constant, and we're done. Okay, the next complication that can arise when you do partial fractions problems is something called repeated factors. In other words, you factor the denominator and you have one factor appearing multiple times. This is exactly the case here. So the integral that we're working with in this next example is x squared plus x minus 3 over quantity x plus 1 squared times x minus 1. This right here is exactly the repeated factor. So we have to deal with this a little carefully. Where's my red chalk? Over here. X plus 1 is what I would call in this case a repeated factor. Simply because of the 2 here. Okay. How do you deal with the repeated factor in a partial fractions decomposition? Again, I keep saying this, but it's math. You can do whatever you want as long as it's correct. There's typically a preferable way to deal with repeated factors, and that's what I'm going to show you. So I'll start off exactly the same as I have been. We're looking for a particular decomposition. Here's our function, x squared plus x minus 3 over x plus 1 quantity squared x minus 1 equals, here's what I want to do. Now, on the one hand, the first time you see this stuff, it might be tempting to decompose as follows. I've got something over x plus 1 squared plus something over x minus 1. And then you think, okay, this is like degree 2, or it's the factor is degree 1, but so it's degree 2, so what do I put here? And then I put a constant here. You could do this. It would not be wrong. So could do this. But this is not how I'll do the decomposition. And this is what I wanted to show you, that the preferable way to handle repeated factors is as follows. So let's take this first factor, x plus 1 squared. This is going to generate 2 terms itself. So in total, we'll have 3 different terms, 2 of which come from the 2 repeated factors for x plus 1, the last of which comes from x minus 1, this other linear factor. Okay, so with these 2 terms, what I'm going to do is in the denominators, I'm going to write successively increasing powers of the repeated factor until I reach the total number. In this case, that would look like an x plus 1 here, and then an x plus 1 squared here. So just to give you some other examples of the decomposition here, if you had some stuff like blah 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 over x plus 1 to the 35th, the analog of what I'm doing here is I would have something over x plus 1, something over x plus 1 squared, something over x plus 1 cubed, all the way up to something over x plus 1 to the 35th. So you would have 35 different terms. Okay. This is the preferable way to decompose with repeated fractions or repeated factors. The next tricky thing is, what do I put on top here? If we think about what we've been doing, the degree of the factor here is 1, so the thing on top should be a constant, just like before. What you have to be a little careful about is this expression right here. The total degree is 2. But because I've decomposed this way, I only care about the degree of the factor, not the total degree in the denominator. It's the degree of the factor that matters. The degree of the factor here is still 1. The factor is x plus 1. It's just repeated. But because the factor is x plus 1, which is degree 1, you just need a constant on top. You just need a degree 0 expression. That can be a little confusing. Now again, this is the good thing about math. If you're watching this and you're worried about, oh my God, Joe, I'm really confused. Like, what if I screw up and put a bx plus c? That's fine. You'll just add extra work for yourself, but you won't be incorrect. You'll just necessarily find that that coefficient in front of the x is 0. So a different way to say what I'm saying is we only need to put a b here. If you happen to add other stuff, it's fine. You're just kind of adding extra work. Anyway, for both of these terms, the factor is x plus 1. That's a degree 1 thing. So on top here, I get an a and a b. Maybe one more quick example to contrast this with something else. What if you had a scenario where you had a repeated quadratic factor? A repeated irreducible quadratic factor. The analog of the decomposition here would be two terms of successively increasing power of the factor. On top here, this is a degree 2 factor, so I would need a degree 1 expression. And then in the denominator, again, the total degree here is 4, but that doesn't matter. The factor is still x squared plus 1. The factor is still degree 2, so I only need a degree 1 expression. So I would put like a cx plus d here, etc. Okay. So I've got a over x plus 1, b over x plus 1 squared, and then a linear factor again, so I'll just put a c here. Cool. This is the preferable decomposition for a repeated factor. Then from here, it's exactly the same as what we were doing. Let's clear denominators and see if we can figure out what these coefficients are. So I don't have much room over here, so let me go back over here. So clearing denominators, if I multiply through by the denominator here on the left, as always, we'll get x squared plus x minus 3 equals. Now, on the first a term, when you multiply by the denominator, one of these x plus 1's will cancel, but we'll still have one left. So we'll have a times 1 copy of x plus 1 times x minus 1. On the b term, both of those will cancel. So we'll just be left with x minus 1. And then the c term, if I give myself some more room, the x minus 1 cancels, and I pick up 2 copies of x plus 1. Okay. Here's our equality of polynomials that we're working with. As before, we have a bunch of linear factors here, so the best start is to plug in the roots of those factors. One of the factors is x minus 1, so we could start by plugging in, say, x equals 1. This is going to generate the equation 1 squared plus 1 minus 3 equals, when we plug in 1, this is 0, so this whole term is 0. This whole term is 0, so the only thing that we're left with is c times 1 plus 1 squared. Then after some simplification, let's see, 2 minus 3 is negative 1 equals 2c. So it looks like c is negative 1/2. Okay. Moving on, we've got another factor, which is x plus 1. The root of that factor is negative 1. Let me keep the decomposition up here just because I know we'll come back to it. So let me plug in negative 1. Oh, I felt very weird about this. I see where I screwed up. 1 plus 1 squared is 2 squared. So this should be a 4. So I think this should be negative 1/4. All right, let's see if I can get the next one without any mistakes. Plug in x equals negative 1 into this equation, and what happens? On the left, we get negative 1 squared plus negative 1 minus 3 equals negative 1 here kills off this entire term. Likewise, it kills off this entire term, so the only thing that we're left with is b times negative 1 minus 1. After some simplification, we get 1 minus 1 is 0, so negative 3 on the left, and then negative 2 here. So it looks like b is 3/2. We've got b and c. All we have to figure out now is a. Okay, we're out of linear factors to plug in, so we'll have to do something else. We could do a number of things. Probably I'm going to do the kind of thing that I did in the previous example where I compare coefficients, and I know that I'm looking for a. So I'm jumping between, maybe I should compare the x squared coefficients because I know that I'll get an ax squared. Or we could compare constant coefficients. Let's do that, because typically constant coefficients are pretty easy to compute. Okay, so the constant coefficient on the left-hand side is -3. The constant coefficient on the right-hand side is -a from this term -b from the middle term, and then from the last term we would get a 1 squared over here times c, so plus c. Now we already know what c and b are. It's a little ugly looking. b was 3/2. c was -1/4. So we could multiply through by 4 to clear all the denominators here. I'd get -6 minus 1. Whoops. This is like -7, so add 7 to get -5. And it looks like a, if I did all of this correctly, is 5/4. Okay, so we've found a, b, and c. Now we just have to plug this in here, and then we can do the integration, and then we're done. So using this decomposition, we know that the integral of the function that we began with, this is going to be the sum of the integrals of a over x plus 1. A was 5/4. Plus the integral of b over x plus 1 squared. B was 3/2. And then lastly, the integral of c over x minus 1. C was, I may have erased it, but c was -1/4 here. Okay, c was -1/4, so this is the last integral we have to do. All three of these are very straightforward, and then we're done. So I'll continue up here. Now the constants are a little ugly, but you can just pop them out of the integral. Integrating 1 over x plus 1 gives you a log. So 5/4 times log of absolute x plus 1 plus, now here, an x plus 1 quantity squared, this is just a power rule problem. This is like x plus 1 to the -2. Formally, you could make a substitution here where you call u x plus 1, but then du is dx, so it's just a variable shift, and so we don't have to worry about any funny differential things. So here, you can think about this as just being x plus 1 to the -2. Power rule says 3/2. Increase the power by 1 from -2 to -1. Divide by the new power. And then lastly, we have this final integral, which is another log 1. We've got -1/4 log absolute x minus 1, add a plus c, and then we're done. So the numbers were a little uglier. That'll happen, something to get used to. The main thing to take away from this example is exactly the repeated factors. If you have a factor appearing multiple times, the preferable way to deal with this is to have multiple terms where the denominator has successively increasing powers of the function. Okay, so the next complication that can arise when you do a partial fractions problem is when the degree of the numerator is greater than or equal to the degree of the denominator. This isn't something that I haven't talked about this yet, but it's something you should always keep in mind before you do a partial fractions decomposition. Before you decompose something, the degree of the numerator should be strictly smaller than the degree of the denominator. And with this example, x to the fourth minus x squared minus 1 over x squared minus 1, it's not the case. So what do we do? Before we fix it, let me record that key idea because it's important. Namely, that before doing partial fractions, the degree of the top should be strictly smaller than the degree of the bottom. And if that's not the case, as with this example, your first step is to do polynomial long division, unfortunately. In other words, we first have to just divide these polynomials so that we force this to happen. So if not, or otherwise, I guess I'll say if not, do long division. Okay. So in this problem, the first thing that we'll have to remember how to do is how to do long division with polynomials. It mimics long division with numbers. I'll walk through the algorithm and we'll see what we get. So first, what we need to do is we need to take x to the fourth minus x squared minus 1 and divide that by x squared minus 1. Okay. How does the division algorithm work? With polynomials, what we do is we say, look at the highest degree term on the outside. And the question is, how many times does this go into the leading term here? So, how many times does this go into, I'll give myself some more room, the leading term? In other words, what is x to the fourth minus x squared, divided by x squared? That's the question we want to ask. X to the fourth divided by x squared is x squared. In other words, x squared goes into x to the fourth x squared times. So whatever the answer to this question is here, that's what goes right up here. Okay. That's the first step. After you've answered that question, you take whatever you get here and multiply the divisor. So I'll multiply x squared through this term and then write that here. X squared times x squared is x to the fourth minus x squared. So this step came from multiply the divisor by whatever thing you got there. The next step is to subtract. That's the algorithm. And then we just repeat until we're done. In this specific case, when we take this polynomial minus this polynomial, x to the fourth minus x to the fourth goes away. Negative x squared minus negative x squared goes away. So these terms kill each other off, and then we're left with a negative 1. So I'll say subtract and then repeat. So I ask the question again, now using this term. How many times does the leading term here go into the leading term here? It doesn't. So we're done. The algorithm stops here, and this finishes the long division. And let me summarize what we've shown here. In other words, this says that x to the fourth minus x squared minus 1 divided by x squared minus 1, this is, to get a little bit more room, what do we get? We get x squared, but with a remainder of negative 1. So this term right here is the remainder. So this is plus a remainder of negative 1 divided by x squared minus 1. That's the summary of the long division algorithm in this case. So maybe if I use another color, the x squared, whatever expression you get up here, that's what you put right there. And then whatever you get down here is the remainder. That's what goes right here. Okay. Now, to repeat, we had to do this specifically because the degree of the top. Oh, right. This is what we want to have happen. Because this was not true, the degree of the top was bigger, we had to do this long division. Okay. So we've broken up the integrand into two pieces now, and this is the thing here that we can do partial fractions on. But before we do that, let me just integrate the first term. So the integral that we started with, so the integral of x to the fourth minus x squared minus 1 over x squared minus 1 dx. This is the integral of this, which we can break up into two. Integral of x squared minus the integral of 1 over x squared minus 1 dx. Integrating x squared is easy. And so all we have to do is figure out this antiderivative. This is where the partial fractions is going to happen. So I'll continue that over here. But this is the key takeaway from this example, that when the degree exceeds or equals the degree of the bottom, you have to do this long division algorithm first. All right, so over here, I'll just consider the ladder integral. This will be a breeze now. This will be similar to the very first example I did. I look at this and I recognize, the denominator I can factor. It's a difference of squares, so this factors like x minus 1 times x plus 1. The kind of decomposition I would seek, these are just two linear factors. They're not repeated. So this will be something over x minus 1, something over x plus 1. Both degree 1 factors, so we just need degree 0 expressions on top. Clear denominators, so I'll multiply through both sides of this equality by this denominator. On the left, when I do that, I'll get 1 equals. Here, x minus 1s will cancel out, so I'll get an a times x plus 1 plus b times x minus 1. Also, as before, since we have two linear factors here, the best move is going to be to plug in the roots for each of them. They'll give us a and b really quickly, and then we'll be on our way. So when x equals, for example, -1 is the root of this factor, what do we get? We get the equation 1 equals, whoops. When x is -1, this whole term is 0, and we're left with b times -1 minus 1, which is -2. So that tells us that b is -1/2. Then once we plug in x equals 1, we'll get a, and we'll be in the home stretch. When x equals 1, this term is 0. So on the right-hand side, we just have a times 1 plus 1. And on the left, we still have 1. So 2 times a is 1, so therefore a is 1/2. Okay, so here's our decomposition, and what we've shown is that the integral of 1 over x squared minus 1 dx is the integral of a over x minus 1, a is 1/2, plus the integral of b over x minus 1. b was -1/2, so that's the same as subtracting the integral of 1/2 over x plus 1. And so I don't forget, I'll keep this last step up here. If we continue up here, this will be a 1/2 log of x minus 1 in absolute value, minus 1/2 log of x plus 1, plus a constant, and then once we plug that back in here, we're done. So to summarize, the original integral that we started with, which is x to the 4th minus x squared minus 1 over x squared minus 1 dx is, we had this x cubed over 3 term. That came from the x squared term when we divided the two polynomials. X cubed over 3 minus this integral, which is where the partial fractions came into play. So this antiderivative here was this expression. So I'll just pop this in these parentheses, and that'll do it. Minus 1/2 log absolute x plus 1 plus c. Looks a little funny, but that's the final answer. Done. Again, just to repeat, the takeaway here is anytime you do partial fractions, you always have to ask yourself, is the degree of the bottom bigger than the degree on top? If it is, you can do the partial fractions. If it's not, your first step has to be polynomial long division. Okay, the last complication that I want to talk about with partial fractions problems is not actually a complication of partial fractions itself. It's just something that can happen a lot of times when you do one of these integrals. That complication is that sometimes you might need to complete the square. But like I said, strictly speaking, this doesn't actually have to do with partial fractions. So this is just kind of a bonus example to see something new. Now, let's see what we can do. The integral that we're working with here is x squared plus x plus 3 over x minus 1 times x squared plus 2x plus 2. Based on the previous examples I've done, there are a handful of questions that are good to ask yourself every single time you do a partial fractions problem. One of them is the one that I had just talked about in the prior example, which is the degree of the bottom bigger than that of the top. In this case it is. The degree of the bottom is 3, degree of the top is 2. 3 is bigger than 2, so we're in good shape. We don't have to do any long division or anything like that. The other question that's always good to ask is, can I factor the bottom anymore? Sometimes you might have to factor things yourself. Well, x minus 1 is linear, so I can't factor it anymore. The only question mark is this quadratic term right here, x squared plus 2x plus 2. The question is this an irreducible quadratic factor? Well, you could try to just play around with it and try factoring, and maybe you'll have some success, maybe not. Now, in the previous example, when I talked about irreducible quadratic factors, we had something like x squared plus 1. That was relatively easy to just eyeball and see that it was irreducible. Sometimes it can get more complicated, though. So a good thing to do is to remember, how do we systematically check whether a quadratic is irreducible? You can use the discriminant. Now, what is the discriminant? It just comes from the quadratic formula. So the quadratic formula has this term in it that looks like the square root of b squared minus 4ac. And the point is that if this number is negative, this expression won't make sense, and therefore you won't have any roots. In other words, we can check to see if a polynomial is irreducible by checking to see if this number is negative or not. So the fact is that if b squared minus 4ac is negative, the polynomial ax squared plus bx plus c is irreducible. In other words, it can't be factored anymore. Which is going to be the case here. A is 1, B is 2, C is 2, so b squared minus 4ac in this case is 2 squared, which is 4, minus 4 times 2, which is 8, so it's like 4 minus 8, which is negative 4, or something like that. So we cannot factor this anymore. Let me write that down in my solution. So I would start off by saying, since 2 squared minus 4 times 1 times 2 is 4 minus 8 is negative 4, which is negative, x squared plus 2x plus 2 is irreducible. Okay, well that's okay. We've already talked about how to handle irreducible quadratic factors. What do we want to have happen? We want to decompose our given fraction as it's a curvy divided sign. Two factors. I'll have something over x minus 1. The degree of the factor here is 1, so the expression on top is going to be a constant, which I'll just put a, plus this factor we just determined is irreducible. So we'll leave it there. What goes on top? The degree of the factor here is 2, so the expression that goes in the numerator needs to be a degree 1 expression, which is going to look like bx plus c. There's our decomposition. Now we have to figure out a, b, and c. As usual, I'll clear denominators, multiply through by this, and that'll give me the equation x squared plus x plus 3 is a times this plus bx plus c times this factor gets canceled out now, so multiplied by an x minus 1. Okay. Also, as before, we have a linear factor. So the first thing that I'll do is plug in the root of that linear factor to immediately get a. the root of our linear factor is 1. So if I plug in x equals 1, what equation do we get? 1 plus 1 plus 3 is 5. Equals. This whole expression is 0 because of this term. So then I'm left with a times 1 plus 2 plus 2 is 5. So this is 5a. And ding, ding, ding tells us a better be 1. Okay, 1 down. We're out of linear factors now, so the next thing that I'll start doing to figure out b and c is I'll compare coefficients of both sides. For example, I could compare, to figure out b, I could compare the coefficient of x squared because I see that when I multiply these two terms, I'll get a bx squared. So let me compare the x squared coefficient. On the left, the x squared coefficient is 1. On the right, it looks like there are two ways to get an x squared. One of them was from what I identified earlier, the bx squared. But then over here, there's an a, so I've got an ax squared. The total contribution to the x squared coefficient is going to be a plus b. And then, well, we already knew that a was 1, so that tells us b has to be 0. All we need is c now. I can see that I'll get a negative c as part of the constant term here, so like in the previous examples, I'll check the constant coefficient, or the constant terms. The constant term on the left is 3. The constant term on the right will get a negative c here. And then here, we'll get a 2a. A was 1, so this is 3 equals 2 minus c. C should be negative 1. Okay, and we've got our decomposition. We can plug this in, do the integration. So far, nothing different has happened. We haven't gotten to the completing the square issue yet. Like I said, the partial fractions is subsumed by everything we've done already. So nothing interesting happened yet. So we could say this integral that we care about is the integral of a over x minus 1. A was 1. That part's easy. And then plus this. B was 0. C was negative 1. So therefore, this is the same thing as minus the integral of 1 over x squared plus 2x plus 2. Okay. The partial fractions is done. Now it's just a matter of doing this integral is no problem. This is the one that we might have to think a bit about, and this is where completing the square comes in. So what's the deal? Let me take care of that first one. So continuing from down here, this gives me a log of absolute x minus 1. Minus, and this is what we have to figure out. Okay. How do we integrate something like this? Well, we can't factor it more, so partial fractions is out of the question. A simple substitution doesn't work because if you were to call u blah, 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 you'll have a weird differential that you can't absorb in the numerator. So the thing to identify is to complete the square and try to turn this into like an arctangent or a trig substitution type problem. So let's remember how to complete the square, and then we'll see if it helps us out. To complete the square, what's the algorithm? Whatever the term in front of x is, take this, divide by 2, which in our case, 2 over 2 is 1. That's what you want to add. Sorry, you want to add 1 squared. So 2 divided by 2 is 1, so I'll add 1, subtract 1, because I can't just add 1. That would completely change everything. So I added 1 and then subtracted 1, and then I have this plus 2. So I haven't changed anything in the denominator because that expression is exactly the same as this expression because this is 0. But the whole point of doing this is that this expression now, we've rigged it up so that those 3 terms factor as a perfect square. In particular, x squared plus 2x plus 1, that factors like x plus 1 quantity squared. And then here there's a negative 1 plus 2 that simplifies to plus 1. Now we're in the clear because, again, I remember that the derivative of arctangent is 1 over x squared plus 1. So I can do an easy u substitution here to finish this off. I would let u be x plus 1. Then du is dx. And this integral transforms into 1 over u squared plus 1. Dx is du. And this is exactly arctangent on the nose. So continuing up here, I've got log of x minus 1 minus arctangent of u plus a constant, plug back in for u, and we've got it. Done. Okay. So summary of this example, like I said, strictly speaking, nothing new happened with the partial fractions. The only complication is a lot of times you'll have an irreducible quadratic factor which does not take the form x squared plus a constant. In that case, eventually when you do the integral, you'll probably have to do something like complete the square to turn it into an arctangent looking thing. Otherwise, the partial fractions here is exactly the same.